So in the previous class, we have discussed about the effect of harmonics, power system response characteristics. We have discussed. What are the effects of harmonics? Can anyone tell? Yes. I'm asking you people only. So we have also discussed about the difference between harmonics and transients. What is the difference between harmonics and transients? Don't ask the question. So the transients are actually for the limited period they are going to stay, and for the harmonics they are going to the multiple integer number we are going to call that one, and the harmonics are frequency domain we are going to consider, and for the transients time domain we are going to consider. Only during the load switching on the load and off the transients will produces, but the harmonics will be by using the non-linear components or devices, the loads we are using, the harmonics will be producers. Because of that one, so some harmonic currents, it is going to increase the current. Because of increasing the current, the voltage drop will be occurs. So because, and the load will be increases over there, and by increasing the load, what will happen, the heat will be produces over there. We are going to use the capacitors for the power factor corrections and all the things. So heating increases means the dielectric, the distress will be occurs over there. Some components may get damaged by increasing the temperature. That is nothing but harmonics increases. So these are the effects of the harmonics. Yesterday only we have discussed this all the things. How is some people they will join now? Poonam Homkar. Homkar Poonam. Poonam Homkar. Is it audible or not? Hello? I asked the question, I am taking the name, then also you people are not replying. I am getting a doubt. Is it audible?
Yes, sir.
Okay, thank you. Roll number 11. Roll number 11. Poonam.
Yes, sir.
What is the time, madam? Huh? What is the time now? Borate. Lock the meeting, better option then. So in the next class onwards, what I will do, I'll give up to 5 minutes time only. After that, I will lock the meeting. So anybody, if you came 5 minutes late, means it is not going to enter into the meeting at all. Okay. So the effects and difference between the harmonics and transients we have discussed in the previous class. Now we are going for the discussion of harmonic distortion we are going to call. So in the starting very first of the second unit we have discussed about the distorted waveforms we have discussed about that. How the distorted waveforms we have discussed, that is the straight line is not coming. Okay. So this is the fundamental waveform. Fundamental waveform. This is the harmonics. This one we are going to consider as harmonic one cycle, the two cycle. So fifth harmonic we are going to call that one. This is also not shown those here. One, two, three here now. For the half cycle, three. Next for another half cycle, one, two, three here. So the fundamental frequency, that is fundamental waveforms, that it is running by a one cycle, how much time it is going to take during the same period of that same period time, 1, 2, 3, 4, 4, 5, 6 years now. 6 cycles it is going to complete this one. It is completing the 6 year now. So that one we are going to call this the harmonics here now. So based on these harmonics, how we can draw the distorted waveforms, it will start here like this. I'll start the distorted voltage. I will draw here now. So like this, they are going to do here now. Whatever the harmonics are there, it is going to multiply to the fundamental voltage or waveforms. Fundamental waveforms, it is going to multiply that one. Whatever the cycles are there, here only the fluctuation will occur. So this is the distorted voltage we are going to call that. This one is distorted waveforms here. So like that, the harmonic distortion also, this is called harmonic distortion only we are going to call, because of these harmonics. These are the harmonics. Harmonics here now, and this is the fundamental frequency, fundamental waveforms. Fundamental waveforms, that is called at fundamental frequency the waveforms are running here now. Fundamental frequency, how much it is? 50 hertz is the Indian frequency we are going to use. 4606. Okay, so the harmonic distortion will occur. Why the harmonic distortion will come? Because of the harmonics we are going to use the harmonic distortion. But why the harmonic will produces? By using the non-linear devices, the harmonics will produce us here. Now, because of the harmonics, what is going to happen? The harmonic currents they are going to inject into the system here. So because of the harmonic current injection, so the voltage drop will be occurs or voltage distortion will be occurs over there. So the non-linear devices is nothing but that is which the voltage is not proportional to the current we are going to. Normally, according to Ohm's law, V is directly proportional to I. We have considered that one. But that one which will not satisfy, that is called non-linear. We are going to consider. The linear means voltage proportional to the applied voltage. Sorry, current proportional to the applied voltage, that is called linear loads we are going to call it. So the non-linear devices, the switching devices or electronic devices, whatever it is there, they are going to produce the cycloconverter, inverters, rectifiers, these circuits, they are going to produce the non-linear, harmonics it is going to produce. Because of these harmonics, the current value it is going to increase. So current value is increase, nothing but current distortion will occur. Because of the high current or harmonics, voltage will be dropped, so voltage distortion will occur over there. So those distortions are called voltage. It may be voltage distortion or current distortion. That distortion we are going to call as harmonic distortion only. This harmonic distortion is the combination of fundamental waveform and harmonic waveform EMF, that is give the distortion voltage. It is going to give that. So harmonic distortion is caused by non-linear devices. Non-linear devices only it is caused. Harmonic distortion, that is harmonic voltage or distortion, is caused by non-linear devices in the power system. A non-linear device is one which the current is not proportional to the applied voltage. I told V is not proportional or not, does not proportional, we are going to call that. It is not proportional to I here now. So voltage, current is not proportional to the applied voltage. That is no linearity here now. See here, not proportional. When we are going to call that one, this one, I'll consider here y-axis, x-axis here now. One I will consider as I here now. Another one I will consider as V here now. So both linearly it should have to proportional here now. Jaisa voltage increase hote, as a linearly it should have to increase. But it is not happening here now. For the current, suppose by increasing the current, the voltage, higher voltages we are going to consider. The voltage is dropping over there. It may be drop, or it may be no change in the voltage. It may be higher to the lower voltage, suddenly it is going to fall. So there is no much difference like that. That is non-linear. We are going to call that one. Yes, sir. So that is, it is not non-linear we are going to call here. Linear means that should proportional voltage or current is proportional to the applied voltage here. Now that is linearly it is going to increase over there with respect to the voltage. So with respect to the current, voltage will increases, or with respect to the voltage, current will increases or decreases. That is linearly we are going to call here. So this one, just it is linearly increase we are going to call this one. This is linearly increasing. For the linear decreases also we can consider that one here. Can how it is like this. This is linearly decreasing. Like how the voltage will current will increases. That is this is not linearity. Opposite side we can consider that one. Here 0 say consider k. Like this we can. Initially the high voltage is there, high current is there. Unlike that it is decreasing, then again the current will decrease, just like that, increasing or decreasing. That is both are linearly proportional, we are going to call them. So a non-linear devices is one in which the current is not proportional to the applied voltage. It is not proportional, we are going to call. So the non-linear devices we are going to call them. While the applied voltage is perfectly sinusoidal, the resulting in current distorted. So whatever the applied voltage is there, that is sinusoidal only, but the result, whatever the current is there, that is distorted over there we are considering. Why? The increasing the voltage by few percent. Distorted means because of the harmonic, it is distorted here. So the sinusoidal voltage we are providing, but the current is distorted. We are going to call that one here. No, for this one like this, the distortion will be there. Okay. But what will happen? Suppose I will increase the magnitude of this current here now. I have increased the magnitude of current, then there is heavy change. We are going to call that current in that way. Increasing the voltage by few percent current voltage I have increased means that may cause the current to double and take different wave shape over there. It is volt current is like this. Suddenly it will go like this here. It will the different shape it is going to take that one because this is a distorted current we are going to call here. No, so distorted current means this current has harmonic effect is there here. When the waveform is identical from one cycle to the next, it can be represented as sum of pure sine waves in which the frequency of each sinusoid is an integer multiple of the fundamental. एक cycle से another cycle, if it is different, I will erase all the things. When the waveform is identical from one cycle to the next cycle, it is identical, then it can be, we are going to consider that is the sum of pure sine wave plus some harmonics, that is called integer multiple of the fundamental frequency, that is called harmonics. We are going to call that one frequency of the distorted wave here now. This multiple is called harmonic of the fundamental here. Whatever it is, by multiplying that one, so this waveforms will be like this. It is going to change. That is called the harmonic of the fundamental. We are going to call them. The sum of the sinusoid is referred to as Fourier series. We are going to call it. The sum we are going to call as Fourier series. When the positive half cycle and negative half cycle both are same over there, on that condition, the shape of that one is same. That one we are going to consider. This is the effect of odd harmonics. We are going to call that. It is the effect of odd harmonics here. See here, when both the positive and negative half cycles of the waveforms. How is that again? Both the positive and negative half cycles of a waveform have identical shapes over there. Have identical shapes, same shapes we are going to consider. The Fourier series contains only odd harmonics. We are going to consider only odd harmonics here now. So suppose if the presence of even harmonics are there, so the presence of even harmonics is often a clue that there is something wrong either with the load equipment or with the transducer used to make the measurement here. Now we are going to use the transducers, that is called, which is nothing but we are going to convert physical quantity into electrical quantity we are going to use. So the presence of even harmonics that will cause us the load equipment we are going to call that here. Now if the positive half cycle and negative half cycles are identical shapes, then that one we are going to consider as, we can assume that is it has only odd harmonics. If both are not identical, then we can consider that it is a even harmonics we are going to consider. So this is the harmonic distortion we are going to call this one. This is called harmonic distortion here now. So harmonic distortion means normal, it may be current distortion or it may be voltage distortion we are going to call. It may be current or voltage. You can consider current and voltage you can consider here. So total distortion, harmonic distortion we are going to consider. Next we will go for the distortion voltage versus current distortion we have to compare here. See, the distortion also it is going to help to measure some controls and all the things. Okay, so we can control the, by voltage distortion we can control the firing angle. From the current harmonics, what it is going to do, we can check the device's rating that one. If the suddenly current distortion is nothing but there is a spike in the current, high current will be applied. what is the rating of that device, if it is damaged or not, how can it is going to sustain that one. So by creating some practicals and all the things, we are intentionally going to create the harmonics over there to test the devices over there. So some that places we can consider that is the harmonics are great, we are going to consider over there, because that will the manufacturing companies and all the things, they are going to create harmonics, they will test it, then they will pass that one. So two, they are going to decide the ratings of that one and all the things over there. So on that situation, it is great also, harmonics are great, or distortions we are going to call it. Same thing we'll discuss here. The harmonic voltages are too great here now. Why? For the control to properly determine the firing angles here now. So in a speed control, we are going to do, we are going to use the rectifier, that is SCR, thyristor controlled bridge rectifiers we are going to consider. On that condition, the firing angle we are going to measure that one. The firing angle, if we have given this one, then only on that period after that one, it is conduction period, and firing angle we can call that one. So this properly we can determine the firing angle by using a voltage distortion or voltage harmonics here. Call that one. Similarly, if we are using the voltage harmonics, that is useful for the control and determine the firing angles. Then what about the current harmonics? The current harmonics, they are going to use to fix the capacity of a device, some devices capacity, the rating they are going to fix over there. So the harmonic currents are too great for the capacity of some device in the power supply system, such as the transformer capacity, and machine must be operated at lower than rated power. On that condition, we can say that one, the harmonic currents are too great, we can say that one. And even the harmonic voltages are too great because the harmonic distortion will be caused by the harmonic current voltage. So because harmonic currents produced by the device are too great for given system conditions, they are produced by the system conditions. So for that reason, those the devices we are going to consider as those are also too great, we are going to consider. That's just these three are the sentences or statements we can call that one here. Next, actually we'll discuss here now with loads how we can increase, what we have to use, that one we can consider here now. That is just general introduction we have discussed there. So nonlinear loads appears, that is nonlinear devices or loads we are using that appears to be sources of harmonic current here. The sources of harmonic currents are nothing but nonlinear loads. So what it is going to do, it is going to inject or increases the current, harmonic currents it is going to inject in the system. So the current is injecting into the transmission line. At this point, the harmonics are there. So here the current I is injecting means this one we can consider as current source also. This providing the high currents here now. Some places in the laboratories and all things it is going to use only. So we can assume that it is a current source here now. Yes, we can assume or not. So like that we have to only the harmonics means we should not think negative also. Some places those are useful also. Just a minute. So with nonlinear loads appears to be harmonic sources of current in the sense with injecting harmonics current into the power system. They are going to inject a harmonic current into the power system. For nearly all analyzers, whatever all the analysis previously they have done, all the researchers, whatever the analysis they have done, based on that, we can say that it is sufficient to treat these harmonics producing loads simply as a current sources here. It is sufficient to treat whatever the harmonics are there, these injecting currents, that one simply we have to treat this one as these loads we can treat this one as producing load, harmonic producing loads. That one is nothing but as a current sources we can produce that one. We can sufficient, we can treat that one here. So voltage distortion is the result of distorted current here. Now, if the current is distorted, because of that, the voltage distortion will occurs that one here. Okay, result distorted current passing through the linear circuit. The whatever the harmonic current or distorted current that is passing through the linear circuit or series impedance of the circuit, that one it is going to cause the results that voltage distortion it is going to result here. Now through the linear circuits series impedance of the power delivery system, although assuming that here, now see here, assuming that the source bus is ultimately pure sinusoid here, whatever the source bus is there here, this is the bus. We are going to consider here the generator here. Okay, somewhere the here load is also connected here. Now load is connected here. Now in this, because of this load, the harmonics will produce us. This bus, whatever we are considering here now, source bus, right? Assuming that the source bus is ultimately a pure sinusoid, there is a non-linear load here. Now we are going to add, instead of linear load, we are going to add a non-linear load. What it is going to do, non-linear load? It is going to absorb, it is going to draw that distorted current here. Distorted currents are produced because of the harmonics only. Because of the harmonics, it is produced here now. So those harmonics, this non-linear load, it is going to absorb that one here now. So just we are assuming that, just think that one, assuming that the source bus is ultimately pure sinusoidal. Why it is pure sinusoidal? Because a non-linear load that draws the distorted current here now, whatever the distorted current is there, it is going to draw this, it is going to draw this distorted currents here now. So the harmonic currents are passing through the impedance of the system. Whatever the harmonic currents are there, those will pass through the system impedance of the system that causes a voltage drop here now. So it is going to reduce the voltage drop for each harmonic, first harmonic, second harmonic, or for each half cycle, the harmonics are there. It is going to reduce the voltage over there. So the harmonic currents passing through the impedance of the system cause a voltage drop for each harmonics. It is going to cause a voltage drop here. So by voltage drop occurs means what it is going to happen here now? This results in the voltage harmonics appearing at the load bus here now, where the load is connected at this load bus. Whatever the voltages are there, these are non-sinusoidal because this is the affecting of voltage distortion will affect that. This results in the voltage harmonics here now. Voltage harmonics, that is called voltage distortion, will occur here now, appearing at the load bus here. Here the voltage distortion or voltage harmonics is appeared here. It should be noted that the load has no control over the voltage distortion. This load is there, it doesn't have any control for the voltage here now. Voltage distortion ka control a load ko nahi hote. This is called the voltage distortion we have discussed here. The same load put into two different locations. Suppose we have placed one bus here now, one load we have placed here now, same load we have placed in two different locations here now. Okay, here one load and here one load I have added here now, different locations I am going to add that one of the power system. This will result in two different voltage distortion value here. This value of the voltage distortion is separate and this voltage value distortion value is separate. It is going to produce two distorted voltage values. It is going to produce that. So this is the voltage distortion and current distortion. We are going to call that one. The difference between voltage distortion and current distortion. Okay. So the next one, that is complete. Still it is there. According to the IEEE standard, we are going to call here now. IEEE standards, that is IEEE standard 519. That is number is there. In the year of 1922, they have implemented this standard here. So it recommends that recommended practices and requirements for harmonic control in electrical power system. They have given two statements here now. According to the IEEE standard 519, So the control over the amount of harmonic current injected into the system takes place at the end use application. This end use application we will discuss in the later. This what it is going to do according to this analysis. They said that the control over the amount of harmonic current injected into the system, whatever the amount of harmonic current injected into the system, that control we can take place at the end use application. We can do the control of that harmonic here, harmonic current injected here. Now that one we can take the control for, that is end use application. We can do that one here. The second statement, that is called assuming the harmonic current injection is within reasonable limits here. We have to assume that the harmonic injection current is reasonable limit. We can consider that one here. Now within some limits we are going to consider that this limit here. Now some reasonable limits we are going to call. The control over the voltage distortion is exercised by, we have to exercise a voltage control, that is called voltage distortion control. We can exercise by the entity having control over the system impedance here. Now by controlling the system impedance, we can control the voltage distortion here now, which is often utility side we are going to do here. That is end use application, one current we can control here now, and by using the utility side, by controlling the system impedance, we can control the voltage distortion. We can control that one here. So these two statements are given by IEEE. They have given that one. So IEEE standard, they have given that one here now. According to the IEEE standard, we have used these two control of voltage control. We can do by using a end use application, and the current injected current, that is harmonic injected current, will be controlled by a end use application, and the harmonic voltage distortion or voltage, that is controlled by a controlling the system impedance at the utility side. We can control that one here. So this is the voltage and current distortion. Some indices are there. Those indices are, that is called harmonic indices. We are going to call them. So in the starting, in the first unit, we have heard the name of total harmonic distortion and total demand distortion. These two are the harmonic indices actually. These two are the harmonic indices. We are going to call that one. Indices, we are going to call that one. So just we have to calculate that one. How the total harmonic distortion we have to calculate, and demand of distortion we have to calculate that one here. So the TSD is nothing but total harmonic distortion. It is the ratio of RMS value of the harmonic current value to the fundamental quantity, that is called TSD. We are going to call that one. And for the TDD is nothing but it is the ratio of RMS value of the harmonic current to the load current or rated current. We are going to call that one. That is called TDD here now. See, this TSD is nothing but total harmonic distortion. It is the ratio of RMS value of the harmonic content, not current. That is called content. We are going to call that one, to the fundamental quantity. We are going to call that one. But the demand it is going to consider based on the current only. It is the ratio of RMS value of the harmonic current to the maximum current or rated current. We are going to call that one. This H indicates this is harmonic here. No, L indicates that is called rated load. We can call that one, or maximum demand. We can call that one here. So the square root we are going to consider that one here now. Square root of that summation of I1 to the IH we are going to consider. So harmonics, that is one more than one or greater than one we can use, or directly we can use 2 here. Here the greater than 1 we have used here. See here, harmonic distortions we are going to discuss. The two most commonly used indices for the measuring of the harmonic content here. Now we are going to measure the harmonic content of waveform are total harmonic distortion and total demand distortion. There are two most commonly used indices are there. One is total harmonic distortion and another one is total demand distortion. Both are measures of the effective value of waveform and may be applied either voltage or current here. We can consider that may be voltage distortion or current distortion. That is not necessary here now. It may be voltage or it may be current distortion. But we are going to perform the two indices that is called TSD and TDD here. So which will give the effective value of the waveform. It is going to give that here. Both it may be voltage or current waveforms. You can consider that. Next one, we'll consider the first one here now. That is called total harmonic distortion. That is called THD. We are going to call that one here now. So the TSD is a measure of the effective value of harmonic component here. We are going to measure the effective value of harmonic components of the distorted voltage or current. Here we are mentioning that is waveform only. This waveform, it may be voltage or current here now. That is, it is a potential heating value of harmonics relative to the fundamental here. Whatever it is nothing but it is a potential heating value here now. Heating value that is relative to the fundamental value, fundamental frequencies or fundamental values they are going to call it now. This index or indices can be calculated for either voltage or current waveforms. Again, they are saying that is it is calculated for either voltage or current here. The exact definition of TSD is we have mentioned here now. Here the ratio of the root mean square, the RMS value we are going to call root mean square of the harmonic content here. No, it is not a current, harmonic content to the RMS value of the fundamental quantity here. This M1 that is called RMS value of the fundamental quantity we are going to call that. The fundamental quantity is nothing but for the fundamental frequency here now. Expressed as percentage of the fundamental here. Now, this one we are going to express as percentage of the fundamental. We are going to express that one. So that is called THD, total harmonic distortion, equal to square root of the summation with limits of IL, that is called greater than 1, that is called IH, that is called harmonic current, that is nothing but that is maximum we are going to use is that is MH square divided by M1 here. This M is nothing but that is quantity here now. H is nothing but harmonic quantity, harmonic component we are going to call this. This is M is quantity, the harmonic component that is called H we are going to call here now, where MH is the RMS value of the harmonic component that is called H here now. Harmonic component is H of the quantity M here now. H of the quantity M, and this M is nothing but that is fundamental quantity, RMS value of the fundamental quantity we are going to call that. So the RMS value of the distorted waveform is the square root of the sum of squares we are going to call that one. That is called square root of sum of this summation we are going to use sum of squares, that value we are going to consider that one. This is the one indices or index, that is total harmonic distortion. That is nothing but total harmonic distortion. हम भी कितना बार ज्वाइन हो जाते आप दीपक? दीपक हम भी 3 times हो गए अभी. I'm admitting again you are leaving. I'm admitting again you are leaving. दीपक हम भी has not joined the audio. कोई तो रिप्लाई दे दो, कंटिन्यूअसली 1 hour स्पीकिंग So next one, the second indices is that is called total demand distortion. We are going to call that. That is called total demand distortion here. What is the demand of the distortion here now? How you have to calculate that one here? So total harmonic distortion kitna hai? That is called how much harmonics are there. That one, that is TSP. How much demand of distortion is there? Based on that, that is we are going to discuss. That is called total demand distortion. That is nothing but the definition of this one is the ratio of RMS value, that is called root mean square of the harmonic current here now. See here only while confusing you will get that one here now. Here harmonic current is there, here harmonic content is there here. While writing the definition, that is the confusing part here. Harmonic current to the RMS value of the rated or maximum demand of fundamental current here. This is the fundamental current we are going to consider. Maximum demand of fundamental current, that is called expressed as percentage. In the percentage we are going to express this, all the things. So the formula for this one here, TDD, total demand distortion, is equal to the square root of sum of, that is I1 equal to, that is IL equal to lower value, that is called 2 here now, and H, that is called harmonics maximum value. This is not IL, this is H here now. The harmonics, that is 2. It may be greater than 1. Whatever the fundamental is there, that one we are considering as 1 only here now. Multiplication of 1 here now. So this one also we are going to call that one as interharmonics. We are going to call this one. This is 1. For that reason, if the harmonic content is greater than 1 only, we are going to call that one. That is H equal to 2, or it may be greater than 1 also, you can write that. If it is greater than 1 to the max here now, that is multiple of integer numbers we are going to consider. That is called IH square here now. Harmonic current, IH is nothing but harmonic current. It's square, harmonic current square, divided by, that is rated current of the fundamental here. Rated or maximum fundamental current here. That is called IL here. So these two questions are, two definitions are very important. I am telling that one. The second unit, the definition part and the formula is, this is the only one I think. So you peoples, I told the remembering the ratio of RMS value of the harmonic content and harmonic content to the RMS value of the fundamental quantity. That is same only you can consider. That is M is the quantity we are going to call, that is fundamental quantity. This is harmonic content and this is harmonic current we are going to call that one. The denominator is same, we can write that one. M1 IL, that is nothing but here also the fundamental quantity, here also the, instead of quantity, that is called fundamental current we are going to consider here. Quantity means M, current means I, we have to consider that. So this much difference we have to remember. This is very important question in the main examination also. So these two are the harmonic indices we are going to call here now. These two are the harmonic indices. And the next part, that is called resonance we are going to call, I think. No, interharmonics we are going to call that. So interharmonics are nothing but, it is multiple of non-integer multiple, that is called, not a integer number here. We are going to call that is not a integer multiples of the frequency. Normally harmonics means what we are going to call, it is a multiple of integer numbers, but it is not integer multiples we are going to call that one here. No, so that is maybe voltage or current interharmonics will be there. In the very first, I think in the first unit we have discussed about this same definition, the causes for that one here. The causes is same only, the static frequency, cycloconverter, induction furnaces, arcing devices and all the things, arc furnace and all the things. So which we are not going to multiply the not integer number, we are going to multiply not integer number, that is called interharmonics. If multiple of integer number, that is called harmonics only, normal harmonics we are going to call that. So voltages are currents. Voltages are currents having frequency component. It has some frequency component, but that is not an integer value. Frequency components that are not integer multiples of the frequency here now, not integer multiple of the frequency at which the supply system is designed to operate. They are not multiple, not in not integer multiple means. So that is, there is no change in the fundamental frequency here. The frequency it is going to operate for the 50 hertz only. So 50, that is fundamental. We are in India, we are going to use 50. That is fundamental frequency. It is going to operate that one, at which the supply system is designed to operate. Example 50 or 60 hertz only are called as interharmonics. They are going to call it. So the voltage, interharmonics is nothing but it may be voltage or currents having frequency components that are not integer multiples of the frequency at which they are going to operate at the fundamental frequency here. Those are called interharmonics. We are going to call them. They can appear as discrete frequencies, or that is wideband spectrum also we are going to call them. They are called, this is discrete frequencies also we can appear here now. Interharmonics can be found in network of all voltage classes. Wherever the voltages are there, in all voltage classes, the interharmonics it is going to found that. So the causes for the interharmonics, that is called static frequency converters, cycloconverters, inductance furnaces, and arcing devices. We are going to call them here. So power line carrier signals can also be considered as interharmonics. Whatever the power line carrier signals are there, so that power carrier signals of that lines we are going to call as interharmonics. Interharmonics current can excite quite severe resonances here now. You can quite the severe resonances are there. Resonances, that one we are going to discuss in the next part, I think. Series resonance, parallel resonance, here it is there in the next. We'll discuss that next part here now on the power system. The resonance will also, it may be problem and it may be some because of the resonance only the frequency will change that one. That is called natural frequency we are going to call them. So severe resonance frequency, it is going to excite and quite severe resonances on the power system as the varying interharmonic frequency becomes coincident with the natural frequencies here. Natural frequencies will be, that is the part of that resonances here now. These interharmonic frequencies, when they are going to coincident with the natural frequencies, then the severe resonances currents are it is going to produce that one of the system. They have been shown to affect the power line carrier signal. The power line carrier signals we are going to consider as interline only here now, interline harmonics. So they have been shown to affect the interline carrier signaling and induce visual flickers over there. The flickers it is going to induce in fluorescent and other arc lighting as well as in computer display of the devices. Some computers they are going to like this, the blur systems it is going to use that one. The flickers will occur that one because of this coincidence of the natural frequency and interharmonic frequency. They are going to affect to the interline carrier signaling they are going to affect. So that will produces the visual flicker that will causes the incandescent, fluorescence and some lightnings as well as some computer devices they are going to affect over there. Since interharmonics can assume any values between harmonic frequencies here. Harmonic frequencies in between that one, they can assume any values here now. So the interharmonic spectrum must have sufficient frequency resolution. It should have, must have the some frequency resolutions it should have to have. It should have. So a single cycle waveform sample is no longer adequate to compute the interharmonics here. Whatever the single cycle we are going to consider, the sample single cycle, that is not adequate to compute the interharmonics, since it only provides a frequency resolution of 50 and 60 hertz. It is providing the frequency resolution that is 50 or 60 hertz. The 50 hertz is the fundamental frequency. So that is not adequate. That is no longer adequate to compute the interharmonics. We are not adequate to compute that one here. So any frequencies in between harmonic frequencies lost, the one cycle waveform through, though though is not, my eyes is blinking actually, is commonly used to compute the harmonic spectrum since there is no frequency between the harmonic frequencies here. See, the natural frequencies are the harmonic frequencies we are going to consider. It has some, naturally we are going to consider that one. The devices which is going to, when the, we are going to consider that reactance, capacitive and inductive, they are going to coincidence is nothing but equal, and that consider the capacitive and inductances both have some natural frequencies. If both will come, on that condition we are going to calculate the frequencies under resonance we are going to consider, but they have some frequencies in between that range of that one, the interharmonics, they can choose any values over there. We are going to tell that. So the next class we will discuss about the resonance, parallel resonance, series resonance here now. This part that is very interesting. Why we are going to call that one resonance? The series circuit, what, how the resonance will occur. Parallel circuit, how the resonance will occur. What are the effects it is going to get to the power systems? That one we are going to discuss in the next class. So some in the harmonic distortion we have considered that one. Evaluation how we have to do. According to IEEE, they have mentioned that is end users, utility, and point common coupling here. Now these 2 points we will discuss in the next class. Just a minute, I will take the attendance. Only 30 students are present out of 66. In that 30, I am also one part. So 29 only. Okay. We'll stop here only and we'll continue in the next class.